Okay, good morning class. So we start the tutorial session today. So I guess in the lectures last week and the previous weeks you start to learn about estimation. So we'll work on some of the questions in this worksheet about estimation. So probably we may start with relatively harder problem like question number 3. Okay. So maybe you can spend a little time to work on this question if you didn't do so yet. If you have completed this, you may try to work on the other question like question number 5 and 7. Okay, maybe let me guide you through how we can work on this question. Now, this question is about whether an estimator is biased or not. So first of all, you need to know what it means by biased and unbiased. An estimator is unbiased if the expectation of this estimator is equal to the parameter you want to estimate. So what we need to do is to find out the expectation of the estimator. Whenever you are asked whether an estimator is biased or not, you need to find its expectation. So in part 1, we are asked to show that the sample mean is biased estimator of delta. So we need to first find out the expectation of the sample mean. According to the property of random sample, expectation of the sample mean is equal to the population mean. So we need to find the population mean in terms of the unknown parameter delta. And because we are given the probability density function of the population, so what we need to do is to find out this integral. This is the general formula to find the population mean. The integral is multiplied with the probability density function, integrating with respect to x. So we substitute the probability density function into the integral, and the integral range will be the range of the distribution, and in this distribution x must be greater than delta. So it will start from delta to infinity. So the rest will be just an integral problem. And I suppose that you know how to do this integration. If you don't know, then probably you may try to follow. It is based on a technique called the integration by parts. So we have a negative sign, so we just put this in the differential. It will become negative of this integral. And then we apply the integration by parts formula. And we try to do the integration step by step. We evaluate this at infinity, it will converge to 0. We evaluate it at delta, it will become minus delta. So it will become 0 minus delta. And for the next term, it will be also, if you substitute infinity here, it will converge to 0. Substitute delta into here, it will become 1. So at the end, we find that expectation of the sample mean is equal to delta plus 1. And it is not equal to delta. Therefore, the sample mean is not unbiased for delta. In other words, the sample mean is biased estimator of delta. Okay? And in part 2, we are asked to derive an expression for the bias. Now, according to the definition, bias is equal to the expectation minus the parameter we want to estimate. So in this question, we will find that the bias of the sample mean is equal to a constant, equal to 1. And it remains constant. No matter how large the sample you draw. So in this question, in this example, is suggests that if you use the sample mean to estimate the delta, no matter how large the sample you draw, there will be always a bias equal to 1. So you are not estimating the target parameter delta. You are always deviated from it by 1. And therefore, if you want to adjust it to have an unbiased estimation, it suggests that we may use delta hat equal to Sn bar minus 1. So that this will become an unbiased estimator. So sometimes using this kind of derivation, it will allow us to, even if it is biased, we can also modify it into unbiased. Okay. Any question? Okay, now let's move on to the next question, like question number 5. Question number 5 is a typical question of doing maximum likelihood estimation. Okay. So try to work on this question, and if you have any question, just feel free to raise the question and ask me. Okay, let me briefly explain a little walkthrough to this kind of question. Now, this is typical question to find an MLE, the maximum likelihood estimator. Now, we always start with this step, write down the likelihood function. The likelihood function is a function of the parameter, usually denoted by capital L. And it is equal to the product of the probability function at each sample value. So we have xi, where I run from 1 up to n, so we multiply all together for this probability function. And since x follows the geometric distribution, so we multiply all this geometric probability together and simplify it, we get the likelihood function. Now notice the likelihood function is a function of p, it is not a function of x. And usually we'll work on the log scale. So we take the logarithm of the likelihood function to obtain the log likelihood function. And the log likelihood function is usually denoted by using a small letter L. So we take the logarithm of the likelihood function. It will become a simple function to work with. So this is how we can write down the likelihood function and the log likelihood function. This is the first step. And the second step to find the MLE is to find the value of the parameter such that this will attain its maximum. And we can simply use calculus. So we differentiate the log likelihood function to find the value of p at which this derivative is equal to 0. This is how we can find the maximum point or minimum point using calculus. So we differentiate the log likelihood function with respect to p and set up this equation. Now notice that when we differentiate this with respect to p, we have a negative sign here. So that's why we have the negative sign here. Solving this equation, you will find that p hat will be equal to n divided by the sum of the x. Or we can express it in terms of the sample mean as suggested by the question. So we find that p equal to 1 over the sample mean will be the point at which the derivative is equal to 0. But this is not the end because we need to verify that this is actually the maximum point. Okay? So we need to check the second derivative. So we need to differentiate the likelihood function twice. So we differentiate the first derivative one more time and set p equal to the p hat we determined before to see whether it is negative. If the second derivative is negative, so that means this will be the maximum point. So we differentiate this one more time with respect to p and put p equal to p hat. Now this is the crucial part of this kind of question. After we take the second derivative, we find that the denominator here is a square, this is a square, n is a sample size, so all these are non-negative numbers. So the problem is what will be the sign of the numerator here? The sum of x and n, which one is larger? And this is usually based on the domain of the distribution, or the support of the distribution. We see that x starts from 1 for the geometric distribution. So that means all the sample value must be starting from 1. must be no smaller than 1. For the whole sample, each of these x must be greater than or equal to 1 because it follows the geometric distribution. Therefore, the sum of them must be greater than or equal to n because we are adding up n numbers. Each of them is greater than or equal to 1. So the sum of them must be greater than or equal to n. So in other words, the second derivative is a negative value. Okay? Because we have negative sign here, all these are non-negative numbers, and this one is also non-negative numbers. So this verifies that this is the point at which the Lido function or the log Lido function attains its maximum. So this is a general step to work out the the MLE when you are given a probability model. Any question? Now maybe we still have a little time, so maybe we can work on question number 7, which is a typical question in which you are asked to find an MLE, a confidence interval. Okay, we have 5 minutes left, so maybe I will just say a few words on how to do this kind of question. So this is a typical question when we are given a normal sample, and we are asked to find a confidence interval for the population mean. Then what we need to do is just to substitute all the information into the formula. Whenever there is a random sample from the normal distribution with unknown mean and known variance, then the confidence interval for the population mean can be obtained by using this formula. In this formula, we need the sample mean, and we have the population standard deviation, which is assumed to be known, and the sample size n here. So in this question, all this information are given. We have the sample mean determined as 100.8. We have the population standard deviation, which is given as 3.4 hours. And the sample size is equal to 9. So all these are given. But in the formula, we also need this quantity. This is the quantile from the standard normal distribution. Now, what does it mean? It is the 1 minus alpha over 2 quantile. And the value of this alpha depends on the coverage. How wide the coverage we require for the confidence interval. So in the question, we are asked to find a 95% confidence interval. So 95% will be corresponding to alpha equal to 0.05. So in part 1, we need to set alpha equal to 0.05 for a 95% coverage. So that we need to determine this quantile. So I just follow the notation from the lecture notes because there are lots of different variations on this notation. Some would like to use this to denote the quantile. 0.975 quantile, which is the point under the standard normal distribution, at which the area to the left-hand side is 0.975. But sometimes you'll see people would like to use this to denote this quantity. In some other reference book, but I follow the lecture notes, so we use this version of the notation. So to determine this 0.975 quantile, we need to use the standard normal distribution table. We look up the table for the quantile, or we use R, just like what you've done in the lab a few weeks ago. So from the table or by using R, you will find that this quantile is 1.96. So once you get this quantile, then everything will ready. A 95% confidence interval for the population mean can be obtained as 100.8, the sample mean, plus minus the quantile, 1.96, multiplied to the population standard deviation, divided by the square root of the sample size. So we will obtain the confidence interval in this form, which is equal to the sample mean plus minus a quantity equal to 2.22. We call this number the margin of error. So you may treat this as a measure how large the estimation error can be if we use the sample mean to estimate the population mean. And this will provide a range of values. From 98.55 to 103.02. Okay? So this is how we obtain a confidence interval for 95% coverage. So this is a range of value we use to estimate the unknown parameter population mean. Now, in part 2, we are asked to find the confidence interval with another coverage. For a 99% coverage, then alpha is equal to 0.01. So that the quantile will be, we are asked to find a 98% confidence interval. So alpha is 0.02, and quantile will be 0.99 quantile. And from the standard normal distribution table of using R, you'll find that this quantile is 0.2.326. So we substitute into the formula again. So that we have the same calculation, except that the quantile used is different. And you'll find that if we want to have a wider coverage, then the margin of error computed will be larger. And the interval obtained will be wider. So this is the trade-off. You want to have a wider coverage, then of course you need to have a wider interval. And usually a wider interval will be less informative because it is less restricted on the value of mu. Okay. Is there any question? This is numerically how we can obtain a confidence interval. Now in this question, it is a pretty simple question because the situation is that we assume we have a long population variance. In some case, we may not have this information. We may not have the population variance. So that we may need to use the sample variance to estimate this. Then the quantile we use will be changed a little bit. Instead of using the normal table, we may use the T table. Okay, this is something that you will learn probably later in the course. So is there any question? Just feel free to raise and let me know if you have any question regarding the course materials. Okay? And there will be no class in the next 3 weeks because we have a Easter break. So we'll meet you again after the Easter break and enjoy your holiday. Okay? So see you later.
Thank you. Have a nice Easter.
See you.